Now, today's lecture will cover logistic regression and midterm summary. I think it makes more sense to include logistic regression as part of the summary. In this lecture, I would like to explain the eighth lecture in the first half and the seventh lecture in the second half. Since we will review all the content so far in the midterm summary today, I will skip the usual review of the previous lecture and only explain the previous in-class report. Okay. No, the fifth lecture was about the k-nearest neighbors method. The k-nearest neighbors method takes k data points closest to the data we want to predict and uses the most common label among them as the estimated label. The k-nearest neighbors was technique that depends on the distance for each explanatory variable. It and so it can be applied to nonlinear cases, so it doesn't always have a linear decision boundary. The the k-nearest neighbors method requires calculating the distance to all data points during prediction, so it uses all training data for prediction. Therefore, large-scale datasets, the distance calculation becomes heavy, making it unsuitable for large-scale dataset. So the third option is the correct answer. Okay, next question. Regarding how to determine k in the k-nearest neighbors method, we introduced the cross-validation. By using cross-validation to determine k, it affects the choice of k. As explained in the second option, cross-validation divides the data into J groups, where each group is treated as test data once and the rest become training data. So it doesn't randomly assign data point to group. Using data for both learning and testing at the same time is out of the question. Uh, whether cross-validation works well for large-scale datasets is unrelated to the number of groups. So the second option is the correct answer. Next is about the NumPy code. The question asks to make the following code output the indices that would sort the values in X from smallest to largest to 1, 3, 3. What should be placed in A? NP dot np.sort creates an array of x values sorted in ascending order, and np.argsort_x arranges the indices when sorted in ascending order. np.beanCount counts the occurrences of non-negative integers, and np.linearalgebra.norm measures the norm. np.argmax returns the index of the largest value in x. Since we want to know the indices when x is sorted from smallest to largest, So we should use the np.args.x. Now, for the practical assignment as usual, so the code involves providing data point, uh, making prediction, and outputting the results. So we just need to replace the data part. So we copy, oh, copy and paste, and we will use here. Here, k is 3, and we want to predict the level of the point np.array minus to 0. So this part is 3, and this part should be minus to 0. So we set k to 3 and run it to get the result 0. So the answer is 0. Okay, that's the last problem asks to predict which level among a circle, close, and uh, triangle will be assigned to the triangle using the k-nearest neighbors method with k is 3. Since k is 3, we need to select the 3 closest point to the triangle. In this case, there is one circle and 2 closes. So the estimated level is close, which has the highest count among them. This completes the explanation of the in-class report for the fifth lecture. Okay, so next, in the sixth lecture, we dealt with decision trees. Decision trees were machine learning models that branch out. They were easy for humans to interrupt by because they made it clear which features were important and how the branching worked. However, decision tree don't always have the highest prediction accuracy, so improvements were needed. Also, the deeper the tree is, the more it tend to overfit the trained data. Additionally, small changes in data could sometimes lead to big changes in the decision tree. So the first option is correct answer. The split at each node of decision tree are made to minimize the impurity after splitting. Therefore, impurity is used as a criterion for splitting data. Also, the features are not randomly selected. While much cross classification is possible, decision tree have the disadvantage of being prone to overfitting. So the second option is the correct answer. Now, for the gene impurity calculation, we need to calculate the proportion of each label. The proportion of level 0 is 2 out of 12. The proportion of level 1 is 8 or out of 12. And the proportion of level 2 is 2 out of 12. So the gene impurity is 1 minus 1 over 6 square minus 4 over 6 square minus 1 over 6 square. So, which equals 1 over 2. Prisoners are using half-wise character. Don't write the answer is 1 over 2 or similar phrases. Just write the number. This is for automatic grading, and if you use wise characters or add extra text, the automatic grading will have problems. I will accept the answer this time, but for the next time I will mark it as incorrect, so please be careful. Next, we have a problem to make prediction with actual data. Similarly, as user, so so data is given, predictions are made, and the results output. So if you copy this and paste, and that is here. Okay. So we reach so so the question. So we obtain this result. So the answer is 0. Finally, the last problem, let's say a decision tree is given as shown in this figure, uh, as shown in the slide. The question asks to predict which level a data point, this one, with these features would be classified into. The future numbering starts from 0. So the second feature is 5. Since 5 is greater than 2.45, we go right the first split. Next, let's look at the third feature. The third feature is 1.9. 1.9 is greater than 1.75. So we go right at the second split. Finally, the second feature 5 is greater than 4.85, so we go right at the last split 2. Therefore, we reach a leaf node with class 2, so the predicted level is class 2. There were no comments that needed responses this time, so I would like to move on to the lecture content. Okay, let me start my explanation about the logistic regression. In this lecture, we will learn about the logistic regression. And the steepest descent method for calculating its parameters. This time we will deal with classification problems. What we want to do with classification is to classify data. Specifically, we want to identify whether an animal in a picture is dog or a cat, or determine whether an email text is spam or normal email. Since we can't compute with raw data, for example, we map image data to d-dimensional vector uh, and labels to 1 or 0. For example, we assign 1 for a dog, a 0 for a cat. This way, we consider mapping d-dimensional vectors 0 to 0 or 1. For example, we have this kind of data. If data is upper right area, we predict it as red, which means 1. Uh, if the data is in lower left area, we predict it as blue, which means 0. In this lecture, we will consider the case where there are only two types of labels. To describe this mathematically, what we want to do is the following. Okay, so given data pairs of image data are xi and label yi, which is 0 or 1, and we have n such pairs. Now, for all data, we want to create a function h that output probability h that outputs the probability. No. So hxi becomes yi almost for many I. Using this function, when we have a new input, we want to predict using h of x. This is a binary classification problem. The function h that appears here is called a classifier. When we actually look at the data, when we actually look at the data, this figure show sorry, no. Anyway, so how do we create a classifier? We have studied nearest neighbor method and decision trees, but at the beginning of this course, we learned a linear regression. You might think, can't we use that linear regression for classification? Linear regression means that when data is given, uh, data is given, we find beta 0 to beta d properly so that beta 0 plus beta 1 x11 plus beta d x1d equals the y1 for all I. However, since y can only take 0 or 1, approximating with a straight line is actually not suitable for classification. When we actually look at the data, for example, like that, this figure shows applying simple regression to one-dimensional data with two labels. However, if you ask whether it can classify well, it's questionable. Therefore, we want to use a function that outputs only values from 0 to 1. So, there is actually such a function. It's called the sigmoid function. Sigma of x equals 1 over 1 plus e to the minus x. This is the definition. And this is called the standard sigmoid function. When x goes to minus infinity, so e to minus becomes infinity, so sigma of x becomes 0. When x goes to infinity, e to the minus x becomes 0. So sigma of x becomes 1. Since the exponential function e to the minus x is monotonical decreasing, so the sigmoid function itself is monotonically increasing, becoming a function that approaches from 0 to 1. If we use the sigmoid function for logistic regression, we might be able to approximate like this. This is a logistic regression. In other words, the blue data on the left side and the red data on the right side were mapping to 0 and 1 respectively. Oh, so this is where. Let's write clearly that logistic regression specifically want to do. Suppose the data is given from x11 to x1d exploratory variables, and y1 is the target variable. For each ice data, sigma of beta 0 plus beta 1 xi1 plus beta d xid. Okay, so we want to make this the probability of yi equals 1. This is the concept of logistic regression. In other words, since we only consider two levels in this problem, this is the probability of being 1, and if we calculate 1 minus sigma, this can be said to be the probability of yi equals 0. In other words, the closer sigma of beta 0 plus beta 1 xi1 plus beta d xid, the higher the probability of yi equals 1. The closer it is to 0, the higher the probability of yi equals 0. This is what the logistic regression we want to occur. Now, let's talk about how to determine the parameters specifically. Here we will consider maximum likelihood estimation. First, we assume parameters beta 0 to beta d. Then we calculate the probability that the given data can be obtained. Then we choose parameter to maximize that probability. Since this alone might be hard to understand, let's go through specific examples. When we have only one data, when yi equals 1, so y1 equals 1, we want to make sigma beta 0 plus beta 1 x11 plus beta d x1d. as large as possible. On the other hand, y1 is equal to 0. We want to make 1 minus sigma beta 0 plus beta 1 x11 plus beta d x1d as large as possible. So, to write this together, the probability that the data is as given is like that. So when y1 equals 0, so y1 equals 0, the first part becomes power of 0, so it disappear, and this part becomes 0. So this becomes 1 minus sigma. When y1 equals 1, it becomes 0, and this becomes 1. So the later part becomes 1. So when y1 equals 1, this becomes sigma. Therefore, we choose beta 0 to beta d to make this as large as possible. Okay. What happens when we have two data points? For the first data point, the probability that the data is as given is as we discussed on the previous page. We can use the same argument for the second data. So the probability that the data is as given become like this. If we assume that the results don't influence each other, these events are independent. So the probability that both things happen at the same time is the predicted product of these two. Product from I equals 1 to 2 of sigma. So like that. So this becomes a probability that both the first and the second data points are as given. So when we have only two data points, we choose beta 0 to beta d to make this as large as possible. In this case, n data point, we just need to change 2 to n. So we aim to choose beta 0 to beta d to make product from I equals 1 to n as large as possible. This function multiplied from I equals 1 to n is called likelihood function. We want to calculate to make this as large as possible, but if we use it as is, this is a multiplication of a probability. So even if all probabilities are large, multiplication means we multiply numbers smaller than 1 many times, like 0.9 times 0.9 times 0.9 and so on. So the likelihood function becomes a very, very small number. Since since it's difficult to maximize this, we consider maximizing the logarithm of this, which is sum from I equals 1 to n, like that. Okay. Or we consider the minimizing problem E of beta, which multiplies this by minus 1 over n. So, So the problem to be solved for logistic regression is to find data that minimize this function E of beta. We would like to calculate this by finding the inverse matrix as we did with the least square method and ridge regression. But just like with last regression, we cannot find the answer easier. Therefore, we use a method that gradually approaches the solution. Similarly to what we did the last regression, here we will use the steepest descent method. Ooh. Okay. The steepest descent method is an algorithm that searches for the local minimum values of a function using only the gradient of the function. The idea is as follows. Okay. Let's assume the function f is smooth. We want to find a point y near a point x such that f of x is less than, so f of y is less than f of x. To do this, we expand the function f around x using Taylor expansion. We get f of y is approximately f of x plus like that. Since we want to f of y to be smaller than f of x, this becomes smallest when y minus x is a negative constant multiplied of the gradient of f at x. To do this, if we allow y to move arbitrarily far from x, the discussion becomes complicated. So let's assume y is very close to x. To be precise, with length y minus x fixed, the smallest value occurs when y minus x is a constant multiplier of minus gradient of at x. When we actually substitute this, it becomes minus df dx ix square. So it is definitely smaller than f of x. So the steepest descent method works like this. We decide on some initial value, x old. From the initial value, we calculate minus alpha times the partial derivative of f with respect to x and subtract it. When we do this, the value here should be smaller than value at the original point. So uh, we repeat this process. When the update amount becomes sufficient small, we terminate. Uh, this this alpha that keeps approaching is called the learning rate. And in the field of numerical computation and physics, it's called the step size. The steepest descent method is also called the gradient descent method in the field of machine learning. To understand why it's called the gradient descent method or steepest descent method. So look at this graph. Uh, this figure plots how x is updated along with counter line. The narrower the counter line, the steeper the gradient. The steepest descent method is an algorithm that update points to drop in the steepest direction. Hence, the name steepest descent method. It's a method that descend in the steepest direction. This steepest direction is a vector of partial, so df dxy to df dxd, which is called the gradient. Since we are descending in the opposite direction of the gradient, it's also called the gradient descent method. When I started talking about the steepest descent method, I mentioned that it finds the local minimum values. What is local minimum? The steepest descent method is reaches valley bottom, descending from the initial value. So there is no guarantee that it's the global minimum of the entire function. In fact, for example, if we consider this fourth degree function, if we start from this point, we proceed to the left side and get trapped in what's called the local minima. This is an avoidable problem with the steepest descent method. But in our case, we usually can't see the entire function, so we can't judge whether that we have obtained is truly the global minimum or just a local minimum. The reason we have been able to find global minimum until now is that for convex functions, local minimum, global minimum. In the earlier lecture, linear regression and ridge regression and last regression from last regression, we only consider convex functions. So we didn't have to worry about this problem. But now it's not so simple. So when applying the steepest descent method or gradient descent method, whether we can obtain the optimal value becomes a difficult question. Let's talk about how to choose a learning rate. A large learning rate makes faster progress, but there's a possibility of not converging due to oscillation. On the other hand, a smaller learning rate has less possibility of not converging and can give higher accuracy result, but it may take time to converge. Therefore, we need to properly adjust to the learning rate. For example, the left figure shows example when the learning rate is too large and cause oscillations. With learning rate of 1.01, it keeps oscillating as value keep getting larger. On the other hand, if the learning rate is too small, there is a problem, hardly any change. Of course, this is because we stop the calculation midway, but if we increase the number of calculations, we would eventually reach the minimum. It just takes time. There are many methods for determining the learning rate, such as Newton's method and the quasi-Newton method, but we will omit them here. So now that we have talked about the steepest descent method, let's apply it to logistic regression. If we denote the matrix X like this, then beta 0 plus beta 1 x1 k plus beta d x dk can be written as x beta subscript j. So the content inside of sigma parentheses can be written as x beta. Therefore, E of beta equals E beta. So we obtain like this formulation. Okay, so next we differentiate this. When we differentiate this with respect to beta I, so J's component of x beta is like this. So what multiplies beta I is xji. So when we take the partial derivative with respect to beta I, it becomes xji. Then using the chain rule for derivatives, we differentiate log sigma. The derivative of log becomes reciprocal. So sigma appears in the denominator. Next, the derivative of sigma appears, which is sigma prime. Finally, the derivative of x beta subscript j appear, which is xji. So xji multiplies in front. Okay. Using this property to continue the calculation, so this property partial so d beta I becomes finally like this becomes finally like that. Okay, so the partial derivative with respect to beta I takes this form. The steepest descent method is an algorithm that can be calculated once the gradient, which is a partial derivative, is determined. Since we have determined the partial derivatives, we have all the tools we need. So the algorithms for logistic regression works like this. Uh, First, we consider the matrix X, which is exponential variables arranged with column ones added at the beginning. We'll also consider the vector y, which is a target variable arranged together. For this, we fixed 1 beta, and so substitute it into the derivative we just calculate, multiply by minus alpha and added this. At this point, so this beta should be smaller than beta old value. So E beta less than or equals to E beta old. So by repeating this calculation, we can obtain a beta. The algorithm for logistic regression is like this. We are the okay. This one. Oh, yes. So the sigma function is defined, then we implement logistic regression. We add column 1 to x, initialize beta with 0, calculate the gradient, update beta by subtracting alpha times the gradient, and check if the update amount is small enough to terminate. We can use, okay, so once, let's take a break. Whee. Okay, let's restart. I forgot to say, so this part changed. So meaning is the same, the meaning is same, but so np dot column stack, np dot one n x like that. So the new version is written that this. Okay, anyway. KOO. Yeah, it is. But, well, okay, so we can use logistic regression is to construct the classifier that we originally intended to create. We predicted that the closer sigma is to 1, the higher the probability of fyi equals 1. And the closer it is to 0, the higher the probability of yi equals 0. The sigmoid function at the sigma of 0 equals 1 half. Since the content inside was beta 0 plus beta 1 xy1 plus beta d xid, if this is greater than or equal to 0, then sigma is greater than or equal to 1 half. Conversely, if this part is so is less than 0, this sigma is less than one half. So, for example, we can construct the classifier is as follows. H of xi equals 1 when beta 0 plus beta 1 xi1 plus beta d xid is greater than sorry, is greater than or equal to 1 and to 0, and h of xi equals 0 when it's less than 0. Here we divided at 0.5, 1 half, but of course it doesn't have to be 1 half or 0.1 half. We can use value other than 1 half. Now, when we apply this to one-dimensional data, it looks like this. When we cut the probability 1 half, the part the greater than 1 half nicely correspond to level 1. We can interrupt it as having a high probability of cross 0. For two-dimensional data, so what's good about this is that even when groups are mixed, so this part is mixed. The prediction results can be interpreted as the probability of belong to a class. So in an area greater than 1 half, so this part, we can interpret it as having a higher probability of cross 1. In area less than 1 half, we can interpret it as having a higher probability of cross 0. For two-dimensional data with labels, then we apply logistic regression and plot the decision boundary. It looks like this. The characteristic of logistic regression are that the results are easy to interrupt and we get probabilistic output. We can see the probability of level 0 and level 1 at each point, so it's straightforward since there are probabilities. Also, we can predict which parameters that have the greatest influence. For example, if beta equals minus 3, 10, 1, then the absolute value of beta 1 equals 0, 10 is the largest. So we can predict the first variable x1 might have a big influence. However, the disadvantage is that it takes time to estimate parameters because all data is used for calculation. But the calculation is first when making predictions after the estimation is completed. This is different from k-nearest neighbor. The ways k-nearest neighbors calculation is required every time we make a prediction. But with logistic regression, the prediction itself is fast. Also, as you can see from the figure, this figure, since we divide by lines or planes, it's not suitable for non-linear classification. In other words, if there is a sphere with another level surrounding it, it's difficult to apply logistic regression as it is now. Well, of course, extensions are possible, but at least within the scope of this lecture, logistic regression is not suitable for non-linear classification. Okay, now let's move on to the code explanation. Hey, let me explain the code. First, let's prepare the libraries. Okay, next, let's talk about the steepest descent method. We could write code to handle any case in any dimension, but that would be troublesome. So here we will deal with one-dimensional case where a function and its derivative are given. As I explained in the lecture, what we are doing inside is the first descending, first this part. Okay, so what we are doing inside is first deciding the initial value. Then we calculate the derivative at this point, multiply by alpha, and subtract from x or. The idea is that the value of x should be smaller than the value of fx old. Repeating this for a loop is a basic framework. If difference between x and x old doesn't change anymore, we return x. If we exceed the maximum number of iterations, we return the last x. Here, let's consider x we created as a function. We could write x squared as x times x asterisk 2. So the x double star 2. We need to calculate the derivative manually. We could use automatic differential to have the computer calculation it, but let's do it manually here. The derivative x squared is 2x, so the derivative df is 2 times x. When we decide learning rate and initial data, and apply the steepest descent method. Sorry, I forgot to. Okay. So we get values close to 0. So which means the minimum value is 0 at x equals 0. You might wonder if you might wonder if this is really true. So let's try with different function. Let's consider this function. Okay, so and we calculate the derivative of f. When we run this, it says minimum. So in this case, yes. It says the minimum is at x equals 0. But this is local minimum. So this corresponds to what we saw on slide 18. So this one. So this value. The two minimum is at x equals 3. Since we know where the minimum is for this function, if we start from a different point, for example, if we set start x to 1.5, Now we can confirm that the minimum value is minus 22 at x equals 3. Okay. If we plot the x change with the steepest descent method, it looks like this. The initial point is here, and the gradient is 2x since this is x squared. Uh, at x equals 10, it takes the value 20. So minus 20, which means we move in the negative direction. On the other hand, okay, so we move in the negative direction at this point at the gradient is still negative. So multiplying by minus gives us the negative direction again. By doing this repeatedly, we approach the minimum value. So in this case, 0. On the other hand, if we make the learning rate is too large, like 1.01, we overshoot the minimum and go to the opposite side by repeatedly this. It oscillation and gets larger than larger, like that. So 700. On the other hand, if the learning rate is too small, in this case 0.001, there are the problem that it moves only a little bit. However, this is problem that can be solved by using large number. In fact, we change step from 15 to 500, it looks like this. We If we increase it more, we can eventually reach the minimum value. So when the learning rate is small, we will eventually reach a local minimum, but it may take time. There is also the question of whether we reach the minimum value at all. We might end up at local minima. So we need to be careful about that too. Uh, in the previous example, if we change the 0.9 to 1.5, if we on this side, so here, if we are on this side of maxima where equal to 1, it would go through the minimum and drop down. This one. So this is something we can do because we know the graph. But for example, in this case, like that, if we change 0.9 to 1.5, yes, like that. This is something we can do because we know the graph, but in high-dimensional cases or with general functions, we can't do this. But in such cases, we can imagine whether it becomes a local minimum by looking at this graph. Now, what is logistic regression? It was like this, and the sigmoid function can be written like this. In logistic regression, we first add a column of 1 to x, initialize beta and repeat the calculation. So multiply the gradient by alpha and subtract it. Put that beta into the beta old. So that beta into beta old and repeat the calculation. If the chain, okay, here. So if the change in beta from beta old, the update is small, we break and terminate. The graph of this sigmoid function looks like this. It's a monotonically increasing function that becomes 0 when x is small and approaches 1 when x is large. Given some one-dimensional data, so like this, when we run it, the data with level 0 spreads the negative side on the left, and the data with level 1 spread in the positive direction. When we apply a logistic regression, this part, with a running rate of 0.1, it looks like this. The graph looks like this. Actually, with the logistic regression we obtained around here, the probability is 1. So it's saying the probability of level 1 is high. On the other hand, the probability is 0, saying the probability of level 1 is 0, which means the probability of level 0 is high. As a reference, if we try a linear regression, it looks like this, and whether it can separate the data, well, it's questionable. We can also apply it to dimensional data. Beta is here. The method is same. Method is same. So prepare the data, apply logistic analysis, logistic regression, estimated beta here, and output beta here. Okay, that's the flow of the process. That's all. Now please please work on the in-class report from the last page.